Hi everyone. In this module, we are going to learn about greedy algorithms. So, greedy algorithms are one of the most intuitive algorithms, and many times when we see a problem, we often try to come up with a greedy strategy. Okay, so this greedy strategy, we will learn what is this greedy strategy, and it works for certain problems. It doesn't work for certain problems. Okay, in those problems, you have to use something else like dynamic programming or binary search. So some other technique you have to use if greedy doesn't work. Okay, so many of the problems that we would be doing in this section, you will get intuition that okay, this is how I can approach this problem. Okay, and many of these problems are based upon sorting as well. Okay, so sorting is an important concept that we used a lot in problems involving the greedy techniques. So we will learn what greedy algorithms are, and we'll look at certain examples. So what these greedy algorithms do, they make a choice that looks best at the moment. Okay, it doesn't think about what will happen in the future. It picks a choice that looks best at the moment. Okay, and there is a hope that by choosing this choice, by choosing this local optima, you will end up at a global optima. So what is the meaning of this statement? Let us try to see. So let's say you're solving a problem, you are at some value. Okay, you're standing maybe here, and there is a route. Let's say this is a road that takes you to the end. Okay, maybe you want to reach some location. Let's say this is location 1, this is location 2. Maybe you want to follow one of these paths, and maybe you want to collect the maximum number of points. Let's say you're standing here, so currently we are here. Okay, and suppose if I go to this path, I get an immediate reward of +5. Okay, but if I go here, maybe the reward is +50. Okay, and here the reward is, let's say, 0, and here also let's say the reward is 0, but at this point the reward is, let's say, +100, and here it is +10. So now if you have a problem like this, the greedy strategy will fail. Okay, so I want to pick which path is the best. Okay, so what this greedy algorithm will do, it will look at what is the best path, what choice is locally best. So standing at here, you can see, okay, this choice gives me a reward of 50. So this is like a local optima. Okay, out of two choices, +5 and +50, I will go with +50. That means you entered this path, then you get +0, and then you get +10. So overall reward that you got is only 60. But if you have followed this path, okay, you would have got a reward of 105. So greedy only looks what is the immediate best choice. Okay, so in some problems, this path can lead to an optimal solution, but in some problems, this might not lead to an optimal solution. So what do you have to do? So some problems where this path leads to an optimal solution, we call that, okay, we'll only follow the greedy path. For example, if you have multiple choices from going from here to here, you will pick the choice that looks the best. Okay, you don't see what entire path would yield, but you pick what choice is the best. Okay, the immediate choice. Whereas if you use something else, if you use something like a DP based technique, what you will do, you will explore the entire paths, and you will say, okay, this path says I will give you a reward of 105. You will explore this path, you will say this path says I will give you a reward of 60. Then you decide. Okay, so in DP, you will spend more time, but you always get the optimal answer. Okay, so in greedy, though it is efficient, but it can lead to wrong answers in certain problems. But in this module, we will see a lot of problems where you can apply greedy and still get the correct answer. Okay, so the first problem that we will take up in the next video is coin change problem, and we will show you the greedy and the DP version of this problem. Hi everyone, so let us talk about the coin change problem. So what is this coin change problem? So firstly, we will discuss the coin change problem in the Indian context. Okay, so if you are from India, or if you have traveled to India, so you might have seen that in India, the currency follows the following denominations. We have a 1 rupee coin, a 2 rupee coin, a 5 rupee coin, a 10 rupee note, 20 rupee note, 50 rupee note. 100 rupee note, 500 rupee note, and a 2000 rupee note. Okay, so this is the denominations of currency that we have in India. So we want to make change of some Indian rupees using minimum number of coins or notes. For example, if I give you rupees 273 and I ask you, try to break this down, okay, into these denominations by using minimum number of coins or notes. The way we generally do it in India, we will say, okay, we have 273 rupees and we have the largest. Okay, let's discuss this greedy strategy. So what we do, we have 273 rupees and we look at, okay, I can maybe subtract 1 rupee from here and I can make it 272, but I will not take this path. Okay, I will not take this path. I can also do, I will subtract 2 rupees. I will say, okay, I will use a 2 rupee and I can make it as 271 or something, or I can subtract 5, I can make it as 268 and so on. So that means by picking one coin, there are so many options to reduce this value of n. But what we do, okay, so out of all possible options, we will first pick the one that is more closest. So we also actually have 200 rupee note in India that is missing. Okay, that is missing in this array. We have a 200 rupee note in India. So what I will do, I will pick the note that is as close to as this value. So that is nothing but kind of a lower bound of this number. Okay, or the number which is less than or equal to this value. So that is 200. What we say, okay, we will take a 200 rupee note and we will subtract 200 out of it and we are left with 73 rupees. Okay, so what is the currency that is less than equal to 73? So clearly we can see we have 50. We'll use a 50 rupee note and we'll subtract 50 from here. Okay, so we are left with 23. So now we want to make a change for 23. So what is the largest note that is less than equal to 23? That is 20. So we subtract 20 out of it. We are left with 3 rupees. So how do we make change for 3 rupees? We say, okay, the largest is 2. So we subtract 2. We are left with 1 rupee. How do we make a change for 1? We pick the 1 rupee coin and finally we end up at 0. So what you can see is that we can use 20 plus 50 plus 2 plus 20 plus 2 plus 1 to make the change for 273 rupees. Now, what is the number of coins that we have used? We have used 1, 2, 3, 4, 5. We can do it in 5 coins or notes. That is the minimum. And you will see that even if you take a lot of examples, this strategy will work with every example. Okay, if it is a Indian currency. Okay, if it is a Indian currency. So we can say the greedy strategy works really well with the Indian currency. Okay, but it might not work with some other currency. Okay, so what we need, so the easiest way of proving that the greedy strategy is going to fail is to find a test case on which the greedy algorithm fails. Okay, but for the Indian currency, you will not find a test case where this approach will fail. It will satisfy for all possible denominations. Okay, so what you can do is every time you know what is the best choice. Okay, every time you need to make a choice, you know that, okay, I just need to find a number that is just less than or equal to the current value, and that's it. That is going to solve the problem. So this is the case of Indian coin change, and now we'll discuss this problem in general. Okay, in the next video we'll see that in what cases the greedy strategy can fail. Hi everyone. So now let us see a problem when the greedy can fail if we talk about some other currency. Okay, let us say you go to some other country and where the currency denominations is of this form. You have a 1 rupee, let's say you have $1 note, you have a $7 note, and let's say you have a $10 note. Okay, and for example, now you want to make a change for $15 using minimum coins or minimum notes. So if you try to apply the greedy strategy here, okay, so what this greedy is going to do, it is going to say, okay, if you want to make $15, I'll first find out what is the largest denomination less than equal to $15. That is $10. So you subtract 10 out of it and you're left with $5. How do you make a change for $5? So clearly the number that is largest, which is less than equal to 5, is nothing but $1. So you subtract 1, it becomes 4. You again subtract 1, it becomes 3. You again subtract 1, it becomes 2. You again subtract 1, it becomes 1. You again subtract 1, it becomes 0. So finally at 0 you stop. Now how many dollars you have used? Okay, how many coins you have used? So you used a $10 coin and you used 5 coins of $1 each. Now this strategy clearly failed. Okay, it's a case of a complete failure. Okay, we are not getting the optimal solution. Okay, so what could have been optimal solution? So the optimal one could have been that, okay, if we have $7 and $1, so clearly we can do it in 3 coins, but our greedy strategy gave an answer of 6 coins. So clearly the greedy strategy fails in this case. Now the question is, then how do we find out what is the exact answer? As I discussed, in problems where greedy fails, you have to use something else. So another optimization technique that is very popular is dynamic programming. So now at standing at $15, you have 3 choices. You can make $15 either by using a coin of $1 or by using a coin of $7 or by using a coin of $10. Okay, so you have denomination that is 1, 7 and 15. Sorry, 1, 7 and 10. So we are saying that, okay, if I use $1 to make 15, that means the remaining amount is $14. If I use $7, that means the remaining amount is $8. If I use $10, then the remaining amount is $5. So now these are sub problems. Okay, these are sub problems that need to be solved. We don't know how many coins would be needed to make $5, okay, or how many coins would be needed to make $8. So we will further evaluate all the paths. Okay, we'll further evaluate all the parts. But let us say you need X coins to make $14, you need Y coins to make $8, and you need Z number of coins to make $5. So your answer to make $15 would be nothing but, let's say, f of 15. This would be nothing but, or f of n, this would be nothing but minimum of these 3 values. Okay, minimum of f of 14, that is x, f of 8 and f of 5 plus 1. Okay, you are using one more coin to go from here to here, so it would be minimum of xyz plus 1. Okay, it would be this much. And now how do you get these values xyz? So you get them recursively. You have to solve for the entire path to get the values. For example, 8 will say, okay, I can make a call to 7, or I can make a call to 1, or I can make no other call. Okay, so 7 can make a call to 6, or it can make a call to 0, because if you pick a $7 note, you can end up at 0. Okay, so if you see, one can also make a call to 0. So if you see that this path would be shortest. So from 0 to 7 we need 1 coin, from 7 to 8 we need 1 coin, from 8 to 15 we need 1 coin. So this is going to return 1. This is going to explore this path and this path, and it will take minimum. So minimum is 1. So 1 plus 1 is 2. So it is going to return 2, something like this. And 8 is going to return something like the minimum is 2 and plus 1, it is 3. So you will find out that, okay, if you break it down like this, 177 or 717 or 771, okay, so there would be 3 branches in this entire tree that would lead to this particular answer. Okay, so I'm not diving into this detail, but I'm just giving you an idea. So if the greedy fails, you have to do something else, and this technique we have covered under the dynamic programming section. So if you go and check out my DP videos, you will understand this concept in a lot more detail. So DP is also an optimization technique, though greedy is efficient, but greedy does not work with all problems. DP will give you an optimal answer in this case. Okay, so I guess you got a high level idea of this problem, and that's all for this video. Hello everyone, in this lecture we'll discuss a very famous problem. It is also known as activity selection problem, and the problem statement is like this. It says you are a busy man and you have a big schedule of activities, and your aim is to do as much activities as possible. Okay, so what you're given the start and the end time of an activity. For example, if you want to go for a date with a crush, this activity starts at 1 p.m. and ends at 5 p.m. Okay, if you want to take part in the contest, it starts at somewhere around 1 p.m. and ends at 7:30. So obviously this activity is taking too much of time, and if you do this activity, you will not be able to play Dota, you will not be able to go to date, you will not be able to watch a movie as well. Okay, so you have to make selection of activities such that you are able to do the maximum number of activities. Okay, so let's see the input output format. So in the input you are given 3 test cases. In the first test case you have 3 activities, and followed by you have start and the end times of these activities. Okay, in the next case you have 4 activities, you have the start and the end times of these activities. And like this one we have, I think this is from the example 7 to 9, 0 to 10. So let us note it down. So we have an activity from 7 to 9, 0 to 10, 4 to 5, 8 to 9, 4 to 10, and 5 to 7. So let us see how we can solve this problem. Okay, how we can solve this problem. See, the idea is there can be 3 different options. Okay, so there can be 3 different options, like for example, so clearly if we are doing an activity, okay, we can pick an activity that starts early. Okay, either you can pick an activity that starts early, that means you start doing activities from the early morning, that starts early. So that is one way of thinking, but it will not always lead to the correct solution. Why? For example, there is an activity that starts at 7 a.m. and maybe it goes till 11 p.m. in the night, and in the day you had some more activities that you could have done, but you are not able to do them because this activity you picked up and it starts very early. So hence this approach will give you a wrong answer. Okay, so picking activities such that they start early and they are non-overlapping will give you wrong answer. Okay, then you might think that, okay, let us pick an activity that has minimum duration, that has minimum duration. Now this might seem intuitive, but again, as I discussed, if you want to prove that greedy strategy will work, think of counter cases. Let's say you have an activity from 1 p.m. to 2 p.m. and this activity takes only 1 hour. But suppose you had another activities, one from 12 to 1:30 and another activity from, let's say, 1:45 till 2:30. Now this activity has a duration of 1 hour. Okay, the second activity has a duration of 90 minutes. The third activity has a duration of 30 plus 15. Let's say it goes till 3:30. It is like 90 plus 15. It has 105 minutes. What we are doing, we have sorted activities based upon their duration, and I start picking up activities which take the minimum amount of time. Now clearly if I pick this activity that is taking 1 hour in the beginning, that means I will not be able to perform these 2 activities. Okay, so again, picking an activity that takes less duration will lead to wrong answers. Okay, so again we cannot do this. The third option could be pick an activity that finishes early. That means you first need to sort the activities based upon their finishing time, and then you start picking up activities such that they don't overlap. Okay, so now why this is correct? So see, an activity that finishes early, that means it has a lesser ending time. Okay, it will give you more time to do the remaining activities. Okay, so an activity that finishes late, or an activity that maybe starts here and finishes early, okay, it's not about the duration, it's about the ending time. It's about the ending time. For these activities, this is the start time, this is the end time. So let us try to sort this list based upon their ending time. Okay, so if I sort this list, so I have the activity that finishes first is 4 to 5. Okay, then we have 7 to 9, 8 to 9, let's say 7 to 9, 8 to 9. Oh, we also have 5 to 7, that is another activity. Okay, then we have 0 to 10, we also have 4 to 10, right? What we have done sorting based upon the ending time, that is this digit 5, 7, 9, 9, 10. How many activities we had? So we had 1, 2, 3, 4, 5, 6 activities. So we have drawn a list of 6 activities. Okay, now what I will do, I will say, okay, I'm always going to pick the first activity. So the first activity in the list is this one, so I pick it up. Okay, I pick it up. Let me use a different marker. So I pick this activity. So I've taken an activity from 4 to 5. All right, can I pick 5 to 7 next? Yes, because it is non-overlapping, it doesn't overlap. Can I pick 7 to 9 next? Yes, of course, I can pick 7 to 9. Can I pick 8 to 9? The answer is no. The activity 8 starts from here and it goes till 9. So it cannot be picked up. 8 to 9 is not possible. So we ignore it. Can we pick 0 to 10? The answer is no. We cannot pick it because we will pick an activity that starts after 9 p.m. So it cannot be picked up. Can we pick 4 to 10? The answer is no, we cannot pick this up. So hence in this case we can do 3 activities, and that was the answer. That was the answer in the question, that in the test case that we have seen. Now let us try to apply this. Let us try to apply this logic over this diagram. So if I sort these activities based upon their finishing time, so this activity is the first one to get finished because it ends at 5 p.m. Then the second activity is watching movie. Then in the sorted list, the third activity would be participating in the coding contest. The fourth activity would be Dota. So it ends somewhere around 9:30. The fifth activity would be study for exam, and sixth would be sleep peacefully. So this is the sorted order of lists. Okay, so sorted order of activities. Now we need to find out how many activities can be done. So we will always do the first activities, okay, because that can always be picked up. Okay, done. What is the second activity that I will do? So first I've done that. Okay, I will go on a date with my crush. The second activity, can I watch a movie? The answer is no, because it overlaps with this activity, so it cannot be done. Can I take part in coding contest? No, this activity starts before this activity is finished. Okay, so we cannot do this. Can I go for gaming? Yes, I can play Dota. Can I study for exam? No. Okay. Can I sleep peacefully? Yes. Okay, what a day. You went for a date, you played some games, and you slept peacefully. Okay, so this is the ultimate life. So you can do 3 activities in a day. Okay, all play, no study, makes the jack a stud boy. So you can do 3 activities in this day, and this is how we can solve this problem. Now talking about the implementation, how you can do it. So in the code implementation, you can maintain certain data structure. For example, a list of activities that stores start and end times, and then you can use the inbuilt sort method, and you can give a comparator that, okay, I want to sort these activities based upon the ending time. Okay, so either you can use a list or a vector or a dynamic array. So any linear data structure can be used to store these activities and sort them. After that, you will write the logic to pick and count activities such that the two activities do not overlap. So that's all for the intuition behind this activity selection problem, and I hope you will try to write the code by yourself. That's all for this video. Thank you. Hi, so now it's time to move on to the next greedy problem. It's an easy problem, I would say. So let us go through the problem statement. You can also go through this problem statement on your own. The problem name is biased and it is on the platform Spotch. Okay. So it says the results of competitions are based upon the scores, and we are planning for a change in the next year of ICPC. During the registration, each team will be able to enter a single positive integer. Okay, so they're asking each team a single positive integer which denotes their preferred place in the rank list. Okay, so you ask each team that, okay, what rank you are hoping to get, and you take all these preferences into account, and at the end of the competition an rank list would be announced that would please all of the teams. Okay, but it is also true that we won't be able to satisfy all the requests. Okay, so if multiple teams ask for rank number 2, you cannot give rank number 2 to multiple teams. Each rank has to be given only to one team. Suppose that we already have a rank list. For each team, compute the distance between their preferred place and their place in the rank list. Suppose let's say a team said I'm hoping to get the 3rd rank, but the team gets the 5th rank. Okay, so the difference 3 minus 5, the absolute value of this, it will be called as a badness in this rank list. Okay, so the badness for this team is 2. The given team names and their preferred placements, we need to find one rank list with the minimum possible badness. We have to minimize the absolute sum of differences, the sum of absolute differences between the expected ranks and the actual ranks they get. Okay, so now let us look at an example. So for example, we are given 2 test cases and we have team noobs. So there is team, let's say team expected for a rank 1. There is another team, this team expected for a rank 2, another team expected for a rank 2, another team expected for a rank 1, another team expected for a rank 5, another team expected a rank 7, and another team expected a rank 7. Now we want to create a rank list that minimizes the badness. Okay, so this is what is their preference, but we know that we can only give ranks that are available. So we have 1 2 3 4 5 6 7 teams. So we have actual ranks. The actual ranks will start from 1 2 3 4 5 6 and 7. So we need to allocate these ranks to these teams. So how you are going to do it? The easiest way would be if you do sorting. Okay, if you sort these teams based upon their ranks, so what you are going to get? You're going to get A1, B2, sorry, you are going to get D1. So D is also competing for the first spot. So we should try to give D a rank that is closest possible available. Okay, so we cannot give the first rank because we have given this rank to A. So what we will give? We'll give the next available rank to this team. So D will get a rank of 2. Okay, now the team B expected a rank of 2, but since we are doing sorting, what we can do, we can give the next closest available. So B expected a 2, but we are giving it a rank 3. C expected a rank 2, but we are now giving it a next available rank, that is 4. We have E expected a rank 5, we are giving it 5. We have F, it expected a rank 7, but we are giving it 6. And we have G that expected a rank of 7 and we are giving it 7. Now if you try to find out the differences, okay, what is the badness for this team? So 1 minus 1, it is 0, 1 minus 2, 1, 2 minus 3, 1. So we are taking the absolute difference. Okay, 2 and 4, 2, 5 and 5 0, 7 and 6 1, 7 minus 7 0. This is what the total badness is going to be. So you have 2 plus 1 3 plus 1 4 and plus 1 5. Okay, so in this case you can see the total badness is 5. Now what is the greedy approach in this problem? Okay, so the greedy thinking is like this, that for every team we are trying to give the closest possible rank that is available. Okay, so why this is a greedy approach? Because we are only solving for the current team, we are not solving what would happen to other teams. So at every step we are looking at, okay, what is the next closest rank that has been asked and what is the next closest rank that has been available. Okay, so this is what is asked and this is what is available, and we want to minimize this difference. If you want to minimize this difference, then you have to match the closest asked rank with the closest available rank. Only then you will be able to minimize this difference. Okay, so this sounds intuitive, and yes, this greedy solution is correct. It will work for this problem. You can have multiple test cases. You will find not even a single test case on which this theorem or this approach will fail. Okay, so I hope the coding part is not that difficult. You can do it on your own. So one thing that I would recommend you is, see, there are two ways when you're going to code it up. So definitely this requires the use of sorting. So you can use something like a n log n algorithm to do the sorting. You can also do something like the sort of counting sort to do this. Okay, so what you can do, you can try to think, can I do something on the lines of counting sort, and can I do it in linear time? Okay, so this is a question mark for you to think and answer this problem. Okay, so I'll add a coding video to discuss the solution that is linear. Okay, so that's all for this video. Thank you. Hi everyone, in this lecture we are going to discuss an interesting problem which is known as Defkin. Okay, so defense of a kingdom from the Spodge. So you're given a game and the player has to defend a kingdom that is represented by a rectangular grid of cells like shown in this picture. So the player builds a crossbow towers in some of the cells. So some of the cells have towers, like this is a tower, this is a tower, and this is a tower. Okay, the penalty of the position is number of the cells in the largest undefined rectangle. So for example, the number of cells in the largest undefended rectangle. So what is an undefended rectangle? So the white area that you see, they are undefended rectangles. Okay, because if someone is at the tower, he can look horizontally or he can look vertically. So that means the gray lines are defended. Okay, so the gray lines, they are being defended. So this part is defended, this part is defended by this tower. What we need to know is that what is the largest area that is not defended. So that is what we need to compute. So let us see how we can approach this problem. So let's look at the input. So in the input, what we are given the size of the grid, that is, it has 15 rows and 8 columns like this one in the figure, and it has 3 towers, and we are also given the coordinates of the towers x1 y1, x2 y2, and x3 y3, because for the above diagram we have 3 towers. Okay, and what is the output? The output is a single integer, that is the area of largest unbounded undefended rectangle. Okay, so in this case we have 2 rectangles which are largest. One is this one and another is this one, right? Now given the size of the grid, that is 15,8, and we are also given the position of towers 3,8, 11,2 and 8,6. We need to find out the area of the largest undefended rectangle. Now let us see how we can solve this problem. So if you look carefully, okay, what is creating a white area? Okay, so it is basically the horizontal distance between the two towers. Okay, so if you talk about the length, let's say this is the length direction and this is the, let's say, width direction. What is the length of the white area? So one white area is this patch, so that is the distance between these two towers, T1 and T2. Let's say this is the x-axis, okay, and this is the y-axis. So it is nothing but the distance between x2 minus x1. That is the length of this white rectangle. What is this length? This white, or this white, or this white. What is the length of all three rectangles here? So it is nothing but the difference between the x coordinates of T3 and T2. Okay, it is the difference in the x coordinates of T3 and T2. And what is this length? This length is nothing but it is the distance between ending of the grid, okay, end of grid EOG, and the last coordinate, the last tower, that is x3. So that will give me this length. What about this length? How much is this length? Okay, so this length is nothing but the distance between tower 1 and the start of grid, that is this length. So that means the rectangles have a x length, okay, so delta L, that means how much is the length. The one rectangle has 2 units of length, another has 4 units of length, another rectangle has 2 units of length, and again it has 4 units of length. Okay, so if we know the length and if you also know the breadth, okay, if you also know the breadth of each of these rectangles, okay, then it would be very easy for us to compute the area of the largest rectangle. Okay, so in order to compute this area, what do you need? You need this delta L and you need this delta B, the breadth. So how do you find out what are the various breadths of various rectangles? Okay, so one breadth could be this one, so it is nothing but T2 minus T1, the y coordinate. Okay, so you're subtracting the y coordinates of T2 and T1. What is this breadth? This white area. Okay, how much is this? This is nothing but distance between y coordinates of T2 and T3. Okay, and what is this breadth? It is nothing but T3 and the y coordinate of end of grid. Okay, now I'm writing these down like one breadth is 2, one is 4, and another is 2. Now the thing is, with any length you can combine any breadth. Okay, for example, with this length, that is 4 units, you can combine the length of 1, sorry, this one is 1 actually, the difference between T2 minus T1, so this is actually 1 unit. So you can combine these 4 units with these 1 units as well. Okay, you can also combine this delta L with this delta B. Okay, you can also combine this delta L, which is 4 units, with this one, so this is actually also 1 unit. Okay, this is also 1 unit, and this is actually 3 units. So I just write one thing extra. So this is actually 3 units, 1 unit, 3 unit, and 1 unit, 3 units, and 1 unit. So that means if you look at all these rectangles, okay, so if you have this strip which is 4 units, so it can either go with this breadth, or it can go with this breadth, or it can go with this breadth. So that means any delta L can match with any delta B. Okay, any delta L can match with any delta B. So in order to find the largest rectangle, okay, so area would be nothing but delta L into delta B. So in order to maximize the area, you need to maximize delta L, you need to maximize delta B. So the maximum delta L is nothing but 4, the maximum delta B is nothing but 3, 4 into 3 is 12. So you get the area as 12 units. Okay, now you have two rectangles that have this area. So one rectangle is this 4 into 3, another rectangle is this 4 into 3. This is also 12. So this is a greedy strategy. So what we have done, okay, let us look at what we have done. Important thing is, how do we get these deltas? Okay, 2 4 2 4 and 1 3 1. So let us look at how to compute these deltas. So 2 4 2 1, that is delta L and delta B. So 1, 3 and 1. Now we know the coordinates. The coordinates are 15, 8, 3. 15, 8 is the grid size. Okay, grid size is length of the grid is 15, the width of the grid is 8, and we have cells at the x coordinate of the cells are 3, 11 and 8. We have towers which are located at these positions. X is I just forgot, 3, 11 and 8. So x is 3, 11 and 8. Okay, and what is y? Y is 8, 2 and 6. 8, 2 and 6. So this is for T1, T2 and T3, whatever is these towers. So we don't know. Okay, this is actually not sorted. They're not given in a sorted order. So 3, 8 represents the first tower, which is this tower. Okay, then we have another tower which is 11, 2. Oh, 11, 2 is this tower. Okay, so we have 3, 8. So 3, 8 is this tower, 11, 2 is this tower, and 8, 6 is this tower. So we are not given these towers in a sorted order. So how do you compute the deltas? So you need this tower and this tower to compute delta x. You need this tower and this tower to compute next delta x. You need this tower and end of the grid to compute next delta x or delta L. Okay. So what you can do, you can arrange the x coordinates in a sorted order. So you can say, okay, my x coordinates are, so you also put the starting coordinate, because you also need to know the distance from the start. So starting coordinate is 0. Okay, what is the next tower? Smallest one, which is 3. Okay, what is the next one? 8. Okay, this one is 8. Okay, this one, first is this one, next is this one. What is third? The third is this one. The third is nothing but 11, which is this one. And finally you put the end of the grid. End of the grid is nothing but 15. So how do I get delta L? So it is nothing but 3 minus 0 minus 1. Okay, because when you have a tower, okay, so you can do 3 minus 0 minus 1, which is 2. Then you have 8 minus 3. Okay, because 8 is not included. So you have this tower. So 8 minus 3 gives you 5. But the actual answer is 4, right? Because the 8 itself is not included. So the tower starts, the unbounded area starts from 4 till 7. So 4, 5, 6, 7. It is 4 units. So you do 8 minus 3 minus 1. That is 4. You do 11 minus 8 minus 1, which is 2. You do 15 minus 11 minus 1, which is also 4. Okay, so okay, not at the end. Okay, so this is 11, it is 12, it is 13, it is 14, it is 15. Okay, with the ending position. Okay, with the ending position you don't need to subtract 1. So for ending position you do 15 minus the x coordinate of the last tower. So it is 15 minus 11, that is 4. So you get delta L, which is 2, 4, 2, 4, that we have seen. So we get this 2, this is 4, this is 2, this is 4. Similarly, we need to get the delta y. The y coordinates, it starts from, let's say, 0. Then we have 8, 2, 6. You sort it, 2, 6, 8, and finally it ends at 8. Okay, not an issue. So 2 minus 0 minus 1, it is 1. 6 minus 6 minus 2. Okay, 6 minus 2 minus 1. So it is nothing but 3. 8 minus 6. 8 minus 6 is 2 minus 1, 1. And 8 minus 8 is 0. Okay, so you see there is no area here. So it is 0. So we are talking about this area. This gives you delta B. Now what is the maximum value in delta L? That is 4. What is the maximum value in delta B? That is 3. Hence the area is nothing but max delta L into max delta B, maximum length into breadth, that is 4 into 3, that is 12 units. Okay, this is how you can solve this problem. And I hope you have understood the approach. So you need to sort the array of x, you need to sort the array of y, you need to consider the starting and the ending position as well, and then you need to compute deltas by doing that xi minus 1. This gives you a delta and a minus 1 here. Okay, similar for y, and for the ending coordinate there is this strip is also included, so you don't subtract 1 from that. So I hope the algorithm is clear, and now you will try to write the code by yourself. That's all for this video.